Welcome to today's Propeller Live Forum. It's July 10th, the middle of summer, and it's 1 p.m. Pacific. I'm in Rockland today, and I'm just going to get the meeting started, hang out as long as I can, because I'm here to help Jeff with some things in the office today. And yeah, so we have a couple topics today, and they're kind of all informal. One is that we've got John Huffman, who's going to show us his latest camera controller that he works on using the Propeller. And we have Chip, who has been helping one of our community members with a sonar project, which I think we've talked about here before.
Actually, he's been doing the work. I just have one of his transducers here.
Okay, cool. You'll do the show and tell. And I don't think he's actually online, but if he shows up, let us know. And then Stephen will talk about Peanut-TS. And there's no particular order, but maybe we should do Stephen first and then John and then Chip. Does that sound okay?
I'd be okay with John going first since he's got real product.
Let's do that, yeah. All right, so John, then Stephen, then Chip. And Ari, I'll let you know when I disappear.
Sounds good.
Okay. So John, thanks for being with us today.
Sure.
All right, did I put you on the spot?
No, not at all. I'm gonna try and do this with one hand, but this is my latest Buzz 3, I call it. Let's see if this is working. It's is that backwards? Can't tell.
No, it's okay. Yeah,
That looks good.
we can see it, we can read it.
Okay. So this is based on the flip. You can see it in here. And this is another zoom focus iris controller that I built for different jib operators, different jib companies. There's Jimmy Jib, there's CamMate, those big long camera cranes that you see at concerts and events that have a camera out on the end of them, an operator in the back. It's counterweighted, so they basically just fly the camera around with a couple of hands, and then they have full control of the camera, pan, tilt, zoom, focus. So this this Buzz box with the flip module operates these tiltomotors that are made in China, and they're called Nucleus M. They have little displays on them, and from this controller I can try and do this with one hand. So I can essentially zoom so this would be on a camera lens like this, or a cinema lens, and it would attach to the lens rings, and the operator can actually turn from the back of the jib. They can turn so there's one for focus, there's one for zoom, and there's one for iris. And so it just comes in this little box about the size of a pack of cigarettes. They can control the torque, they can control the speed. It has a 7-pin LEMO connector that goes out to the motors. It connects here. And then on the input side, there's a 2.1 millimeter power in 12-volt connector, an 8-pin zoom, a 4-pin focus, and a 4-pin iris. So that's where the controls connect. And they're actually selling pretty good. The nice part is I've built them for all the different jibs as well as steady cams. You'll see those around as well with guys operating now that they need to operate cinema style lenses. They will use these motors to hook up to the cinema lenses. And like I say, it's the flip, And I love the flip module because everything's on board and all I have to do is add my control electronics. And away we go. And in the background here, I've got my Ultimate One that we showed off a couple of years ago. I've added some new features to it, like now it controls these motors, and it will control the built-in zoom on this lens, so I can operate the Ultimate One and control the zoom. I can put the focus motor on this and control the focus ring. And I can also control gimbals now. And I will turn this guy back on. And with my joystick, I can, this is a small version of what they use out in broadcasts. This is a little Ronin, I forget what model, maybe a Ronin S. And out in the field, they use a Ronin 2, which is a huge version of this that will operate and carry a regular size broadcast camera. So I just use this one for testing. But I've got my little test box here with a joystick and a focus control and a zoom. And that's how I'm operating that. But this one is a P2 Edge module, which is in the control box. It's got a next-gen touch screen and some controls on the front, and then it goes out on a regular Cat5 cable via RS485, which carries the 12 volts and the control signals out to another P2 Edge module that's in the far end, which allows them to also use this as a remote camera, which they can also run this over fiber. And I also have an RF version of it that runs over XB, like the S3B 900 megahertz radio version. So that way they can put this just about anywhere and put this just about anywhere. And as long as they have local power to get 12 volts to this, they can operate whatever camera is at the other end. So that's my Ultimate One running off the P2 Edge. And then my latest one is the Buzz 3, which I call it, because it has 3 functions. And it's running off the flip module. That's pretty much it.
I have some questions.
Yes.
How are you handling all of like the control interpretation? Are you using like ADCs on the P2 or
Yes.
like for your joystick? And
yes, right now we're using like MCP 3208, and I've got 2 of those in the control module. So it's taking all the analog stuff and then piping that into the P2.
okay, so MC3208, that's an ADC converter, right?
Correct.
Have you
So,
tried using just the straight pins?
not in the Ultimate One, but we have, I built something else where we use the smart pins. And I can't remember what it is right now. I think it was a one-off I did. But yeah, we use smart pins on the P2 to be the analog to digital conversion.
Okay, yeah, I think we need to well, I did a lot of work on that about a year ago, refining the A to D so that it's DC true. And we had one thing working with 3 pins that was super clean and accurate and really low noise. The 3208, those are just 8-bit converters, right? Or is it a 12-bit?
I think they're 12-bit.
I think that's an 8-channel 12-bit converter, right?
Correct. And that's the one that I've used forever, like in my P1 controllers that I built 10 years ago.
Yeah.
I just carried those forward because they've been such a workhorse
Yeah, I understand.
for all my joysticks and knobs. The 3208 is what I've really been using. And then John McPhailin told me that the P2, we can eliminate that eventually and just use some smart pens.
Yeah, you could. But it's probably a pretty cheap part anyway, right?
It is,
Like $1 or something.
yeah, buck 80, something like that.
Yeah. And then the
Interesting.
touch screen, is that like its own little module that you're interfacing to?
It is, those are next gen. It's a 3.5 inch,
Yeah, okay.
and it's just got, it takes 5-volt ground and then a transmit receive. And we're just doing TTL to that.
Got it.
There is a Propeller Live forum that Johnny Mac ran like 2 years ago where he showed how to use that display chip. And he did a presentation and has some code out there. And I think it was around Christmas time or so. It was
Yeah, I think I
anybody-
remember.
Yeah, we could find that link. It's on YouTube. Anyway, John Huffman got pretty good at doing this on his own, thanks to John.
Yes.
And
I
now you
still,
have a big
I
display
still,
and a smaller one.
I still need him though.
Oh, you do? Okay.
I
We'll keep
can't
him
do it
around.
alone, but I can do most stuff, like 80% of it. But when I get in the weeds, he helps me with the 20%.
And John, did you mention that you use the XBs there?
Yeah, it's not in this particular version that I've got, but I do. In fact, it's you can see right here, you can see where I don't have it stuffed on this board, but it's got the XB outline for that module right there. So when I do need them, I stuff the board and populate the XB.
Ken, you didn't do any sales pitch. Do you want to mention the sale on the XB stuff?
Oh, well, in regards to John, yeah, we talked about this 2 days ago. Yeah, John uses the 900 megahertz, and we have in stock the 2.4. But yeah, to Ari's question, we're going to be selling those things out at like really dirt cheap momentarily. Oh
And
yeah,
it's
those
on
are
the
already on
screen.
sale. This is cheapest price on the internet if you're looking for XBs, and these are the 2.4 gigahertz, I think.
Yeah, it's on the screen
Yeah.
right now, sharing.
Oh, the long range and the reduced power, which is the short range, are cheaper than anywhere you'll see them. So come and get them while supplies last, and grab a Raspberry Pi too.
Yeah, Raspberry
Also-
Pi right there.
Yeah. So these items that you're looking at that you see from us at greatly reduced prices are post-pandemic. So during the pandemic, there were surplus shortages, and then everybody over-ordered everywhere and every step of the supply chain, and now there's too much inventory out there. But prices are not really dropping except at Parallax because we don't like to sit on things here very long. So you see that we're trying to get this stuff out of our inventory at any cost. Yeah, so Johnny Mac, if you got a source, a need for those XPs, send them my way. We're doing deals. So more questions for Huffman here. It's great, John, how you've been at it now for 10 years. With
You
the
still
Propeller.
really need an SD driver, right?
I do.
So noted.
Yeah, we're glad you finally heard that, Chip. John Huffman is the guy who can reinforce the point if you need
A
him.
guy on the forum has been working on a SD driver that uses 4-bit mode with smart pins.
Oh, cool.
Well, I think he's working on making it like a pluggable thing for the FlexPin VFS, but that's kind of just implementation detail, really. The actual ideas are kind of, there's a lot of funkiness going on with that because there's like two separate data things going on at the same time. It's all very complicated, but when that works, you can pull really good rates from the SD card.
You know what else is complicated and would be really good is the audio over HDMI, right?
Oh yeah, I was working on that as well. No, I was working on that. There's no as well here, but kind of know that sort of. I think I was working on that in like December, and then it just sort of fell off. Would be really good to get back on that. Because I had it basically working perfectly. It basically just needed integrating into a non-test driver. Because the driver I had it in was basically just displaying a static picture. But it could do the encoding, and it could even do resampling if you're generating audio at like a weird rate, because the TV generally wants to have a normal one.
Well, Chip, maybe those will be resources for you in the future because we've still got you scheduled to do a full, complete SD card driver.
Right. Yeah.
Right, yeah. Thanks, Ada. And John Huffman, thank you. Anything else for John? Anyone have any questions about this?
Yeah, I was gonna say I talked to Ken about this the other day, but I can't use the 2.4 gig XPs at the events that these guys do because they're at things like the Super Bowl where on game day that 2.4 gig frequency is just packed with everything, everybody and their brothers on that.
Oh, yeah, the phones are using it, right? And they're spread
Yeah,
spectrum, but they're probably clogging every single channel.
absolutely. So it's even iffy on the 900 meg because those are still ISM bands. And so far, my flight cam guy's control system uses the protected 450 megahertz, where they use a frequency coordinator to assign frequencies to different vendors there. So they kind of get a level of protection. So we may be starting a new project where these XB radios are actually going to be useful for something that's not that's not a control system, but more of a telemetry system. So that's where the XBs will be useful there.
John, I have a question before we totally wrap it up. Were you using the Propeller Mini before the Flip?
Yes, I did. I was doing a land sea bridge for camera control. So I ordered a few of those and did the prototype, and then I built some production ones. And then that's why I asked you about those, and you said you discontinued them, but now I'm just building that product on the Flip chassis.
Good. Thanks for moving over. I had a few other customers asked me about this the other day, and I've just moved them to the Flip. That's where all of our volume was, and we want to consolidate all of our manufacturing into the fewest number of products.
The Mini was nice because of the size, and we could get into a smaller box, but this size people don't seem to balk at this little pack of cigarette size box.
Cool.
But the Flip takes up almost half of the space inside.
Yeah. I think the Propeller Mini sacrificed some IO pins too, so I recall.
Yes.
Not all there.
Yeah.
But it looks like you're using more IOs now.
Yeah, I'm probably using eight or so. So even the Mini would still be fine, but it is what it is.
Well,
It
we're
works
glad
great.
this is paying to keep your air conditioning on. Okay. Thanks, John.
Yeah, thank you.
You're welcome.
Steven, you want to show
Sure.
what?
So I can do that. let's see, announcements. First of all, the spin 2 extension with the tool chain, I'm in final testing of that, and I'm expecting to release that either this week yet or next week. I ran into some problems with flash loaders that I'm chasing, and it turns out that increasing the number of keystrokes that are mapped to your extension is kind of a nightmare when you're trying to work on all three platforms, because everybody has a different sense of which keystrokes are already allocated to that platform. So it's taken me, 3 or 4 days just to sort through keyboard mapping, but it's real close. So I'm testing the actual production build version, and I expect that to be released this week or next. That'll be the Spin Extension 2.3.0 version when I release it. This is the one that auto-recognizes where tools are installed, FlexSpin and Peanut on Windows. And then when any other command line compilers come out, we can add them as well. And so that'll lead me into my next thing. Peanut TS is a command line compiler coming out. And I'll talk a little bit today about how we've moved from implementation to now certifying that the compiler is really accurate in what it's doing and what it's producing, I should say. All right, let's get things off my screen and get things on my screen. And so we are now running coverage testing built in. In the Git repo for the compiler is, of course, the compiler code, but also a bunch of tests which are run against Peanut on Windows, the source code, and we capture the object, listing, and binary files. And then we run it against our compiler. And then we compare those files. Object and binaries are compared at the binary level, and listings are compared at the text level. And we can use them to determine if number one, if we are understanding the syntax correctly, number two, if we're generating the proper code, and three, that our output is identical in all ways to the Peanut compiler. So what you're looking at here is us running through the coverage test code. And for each of these tests, it's compiling the file and then comparing against the files from Peanut. And so you can see in these tests that we have listing files, object files, and binary didn't match. Same thing here. And for this one, just the binary doesn't match, which is an intriguing problem. Where the object was generated correctly, the listing was generated correctly, and the binary is not. And that's because we're working through some version compatibility issues. The coverage report gives us coverage. Just to show you then when we find issues within listing, what are we doing? Here's a case where code generation, where the listing is nearly identical, but we have a failure to generate some code correctly. And in fact, this tells us that we're 8 bytes short on our code generation. And so Chip and I, when we're working on this, we'll chase through what this means and figure out what the values are, and we'll fix the code generation for this particular spin instruction or PASM instructions or whatever. So we're running through the compiler trying to make sure we get all the code generation working perfectly. And so the question becomes then, how do we tell if we've covered all the instructions? And the way we tell this is that can you see the white screens on mine? The white windows?
Yep.
Okay, good. This is a coverage report where the pink and the yellows are things that we haven't exercised in the coverage. Then we added some code, some source code, and recompiled, and now you can see areas like this have now been covered, areas like this have now been covered. This is an exception, so we actually have to generate code that generates that exception. And I have a suite of tests that just repeatedly generates exceptions from having example code, and then these will go white. And so here's a case where we didn't cover this case well, and we'll go back and add code. And so this is what we're chasing, and if you look at our numbers, that's a terrible way to do it. If you look at the numbers, we're 82% statements, 78% branches, 95% functions. And functions will be fully covered probably, but we'll see a threshold But you can see we're already doing pretty well for elements of the compiler that we care about. Instruction generation lives in the resolver, and this will all be over in the high 90s before we release the compiler. So that's pretty much what I wanted to show you. Any questions?
Hey, Stephen, should we go through the exercise of covering that one issue you just pointed out and show them the process?
I don't know that we need to take up the time to do that, but we could. Right now, we're that particular case that I pointed out is actually a problem in our source code processing. I tracked it down. So that's not a good example.
But that's, yeah, that wouldn't be an easy kill.
Correct. It's going to be killed, but that'll be our next effort that we're working on. So so you should be able to see that we are going for 100% binary compatibility of the compile output from PNet to PNet TS. A PNet TS will be distributed as an executable. It's the TypeScript compiler requires a Node.js runtime environment, and we have a way to package that. So there is a Node.js runtime environment packaged up with the compiler, and you download it as a single executable. The single executable now is available for all the platforms, and when you install it on your machine, the new toolset auto locate feature picks up FlexBin, and it'll pick up PNet TS, and it'll pick up PNet. And for any project you're editing in Visual Studio Code, you just tell it which compiler you want to use it with, and then compilation and download is all handled in the new extension for you. So it all becomes quite a nice environment to work in. Any further questions?
I have a comment.
So,
No question. Go ahead.
can I?
Ada?
So it is, in fact, I can file a bug if it's not one-to-one binary identical to what Peanut original does.
We've been filing bugs as we find, because yes, please do. Please file bugs if you find.
Okay, that is good. That is quality.
Yes, and then secondly, I would like to point out something I didn't mention. Ada, you reminded me. Thank you. In our doing this, as we're for certifying, we've actually found problems with 43. They were fixed in 44. We're still finding things now as we compare the two, working in.
Yeah, of course, if something's bugged in the original, then you probably want to do the right thing.
Right,
Yes,
it
exactly.
exposed, we realized there were bugs in the original compiler.
But of course, it's this sort of thing. If you've got enough code, then suddenly the bugs become features. And if you fix them, everything breaks for someone on the other side of the planet. You know. Also, how big is that Peanut TS executable, just out of curiosity?
Gosh, I'd have to look. Let's see what we know. Where am I going to go to look at that? I'm not screen sharing anymore. I don't need to be. I'm just going to go look.
While you poke around,
Yeah,
I know
please.
from standing around on the sidelines, and what you've been doing with Chip is following a very disciplined, results-driven engineering process, and I'm really
Right.
impressed with it. You guys are doing real work, and it's humbling considering the silly business stuff that eats up our time, but it's not unnoticed. It's impressive, you guys.
Oh, thank
And
you.
you're finishing it, and you've been at it for 6 months. I mean, this is a huge commitment.
It has been an effort, and frankly, we've mostly enjoyed it.
Yeah,
It's been a lot of
fun.
fun working together with Chip.
Yeah, Steve's always like extremely patient and good natured. He never has a bad day.
And I like it, Chip, that he follows all the formal practices and you get exposed to them too.
Right. I could
So
learn something.
you can't just do like cowboy coding on your computer. He's got it on his GitHub.
Right. Yeah, well, the coverage tool is kind of interesting. It shows like what lines of our new TypeScript compiler have actually executed. And so you can find areas, of course, that haven't. That's what we're highlighted. But I was realizing we could make a spin tool that does coverage also, just by simulating XByte in assembly code, so that we pick up the bytes, execute them as normal, but simulate the XByte. But then because we've broken in and we're simulating it, we can then hit counters that relate to each bytecode address. so we could figure out, like, have we actually executed has every avenue of execution occurred in the spin code?
Well, the tricky part is actually figuring out where you store that, right? Because there isn't really any memory that unless you just make a whole
Yeah.
duplicate out the whole. Well, if you made it individual bits, which would be very slow, it would be an eighth of the code.
Yeah, I
You
mean, you
can
could do an
simplify it.
8-bit counter that saturates at 255 for each one, or in his case, he's probably got 32-bit counters, but they just increment every time that line or that line gets executed.
Incidentally, I actually wanted to enable coverage for FlexSpin because I've actually ran into like completely dead branches of code at some points. But that's confusing. But Eric never merged the pull request, and now it's bit rotted.
Ah,
Amazing. I think it's still open. And probably with like
Yes.
a merge conflict.
It is still open, but it won't merge.
Oh. Well, I have to re-look into that, I guess, at some point. Maybe it will be better. Yeah. 29 to 53 megabytes. That's quite heavy.
yeah, wasn't it like a couple hundred kbytes, or was it all the stuff around it that makes it huge?
That's all the Node.js runtime environment around it.
I think I've seen the other day, there was like a tiny JavaScript interpreter that can output executables. I think it was literally just called something like TinyJS or something.
Yeah, what's happening is Node.js currently we're at Node version 20 or something. 22 should be coming out late October, and 22 is supposed to have packaging built in which case it'll be these will be smaller executables. But this difference is insignificant for those of us that are running desktops and compiling. So it's performant, it's reasonably performant, so it's a nice thing. The compiler itself is much smaller. Let's see if I can get a number on that.
I think
Yeah,
it
but
was like,
it always irks me, especially because, well, on these Propeller boards, you don't even have 53 megabytes. So it's like you know how much a megabyte actually is, right? And then
Yes, of
where's
course.
all the space going?
Yeah, this is a hosted compiler. I don't know that we plan to run it there. I could easily see us running it on like an ESP module, something like that.
I don't think those have that much memory either.
They might actually, but we'll see.
Surely they don't have like megabytes of RAM.
Certainly don't have megabytes of RAM.
Yeah,
They
this
do
is
have.
not a RAM-based issue. Yeah.
Yeah, I think the flash though tends to be 16 to 32 megabytes.
Okay, then it would be
maybe a bit tight.
Yeah, maybe a bit tight in that case. Let's see here. Oh, here we go. We finally have information on the size. Oh, let's see here. It gets bigger if I want to add the flash loader into the compiler itself. Open up a window, Steve. Please.
the flash loader being which?
Well, when I have to add USB support, then the executable gets blown up with a binary for USB for each platform.
What?
Yeah, if you're going to do a universal binary. If I want to do a platform-specific binary, then you add the binary image for each platform independently. And I come up with 12 different.
You can't just open up a... So in Node.js, you can't just like open up a COM port or a dev TTI something and just write into it?
Nope. Welcome
No
to
IOCTL?
the Node USB serial module.
I'm 100% sure that you can do things like that in even like more complicated scripting languages like Ruby. I distinctly remember being able to do direct Win32 RP calls in there without any native module. So I don't know, I'm confused.
We'll see. We'll see. So far, I haven't been able to find a way to do it. So far, we're using the USB serial module that's available as an NPM package. and that is built with a bunch of platform-specific binaries underneath, because the interface to the devices on the different platforms is radically different. So there's, some things I want to solve and some things I don't want to, and getting into how to talk to devices on specific platforms in specific ways, and recognizing that it's the vid-pid that we need, is a lot lot of effort. And so I
Well, that's the thing.
surveyed
How
all
do
the
you know
USB
that it's a
I
USB
surveyed all
serial
the,
that you want?
say again, please?
How do you know that it's even a USB serial? It's if you have something like a Raspberry Pi, you can just connect it straight through the I/O pins. Pretty sure, like
Anyway,
one of the loaders
that
supports
wasn't
this.
that wasn't a problem I wanted to solve. And so the compiler right now is built without USB support in it, and the extension carries the USB capabilities for flashing.
Yeah, that's sensible. You don't really need the serial in the compiler. It's kind of like separation of concerns.
Correct. And so that's the way we built it at this point. And so I do have the ability to build it in now that I understand the packaging, but I'm not sure there's a good benefit for doing it. And the compiler itself is about 28K. Then you have to add in the objects that get linked in for debugging and for interpreting, and they're a little bit larger. So it's actually a very small compiler.
It's really just small JavaScript, but like big bloatware that needs to run it.
Absolutely.
Yeah, the usual thing.
Yeah. And so the objects that get linked in are all anywhere from 3 to 5K.
Well, when it comes out, we can try making a smaller version.
Yeah, if we need to, but I'm not sure the motivation's there. It'll be fully functional for all of us on any platform as it comes up. When we try and target it to smaller platforms, there'll be a little bit of work, maybe. But either way, it's exciting to use right now, and it's running really well. Compatibility is really high. As you can see, we're just working through the final testing and coverage to make sure we've got every form of every instruction identified and compiling identically. And that, you can imagine, with a processor this size, is quite a bit of work.
Mm-hmm.
But it's been fun. A lot of good work.
Stephen, I have a question for you.
Yes, Grover.
You said that you're wanting to run this on 3 platforms, Mac OS and Linux and Windows.
Yes.
Which versions of Windows are you testing this on currently?
I'm currently testing it on 10 and 11,
Okay.
and it's working well on both.
Good.
So yeah, it's pretty much platform independent because it is Node.js. So it's the Node.js runtime that does all the adaptation to the OS.
Okay.
It's turned out that
Just curious about that. That's all.
yeah, I wouldn't expect problems with the older Windows either, because all we're doing is file operations on the OS, nothing more specific than that, and that's pretty portable in general.
Yeah. Okay.
Cool. Any other questions, Ed? All right, thank you.
Thank you, Stephen.
Thanks, Stephen.
Chip, are you ready for your bit?
Yes. Okay, let's see here. So we have a customer named Dave Conrad, and he has done a lot of stuff in the past with like phased arrays of ultrasonic transducers. So he built this. He spent months getting he lives up in Hillsboro, Oregon, and it's very humid up there. So it took him a while to get his 3D printers to dry the filament enough to produce something like this. But what this is, you can see on the front of this, there's like slots. And I don't think we can see down the holes, but there's little tubes, and they go down and they come back out the backside to these transducers. Let's see if it'll focus. Anyway, so this one has 6 transducers in it, and they're all equidistant away from their horns. So these on the front side here, you have these horns, You can't see them, but they go back and they go to these tubes that go to the transducers back here. So I have this thing wired up in a single-ended arrangement where I have a common ground, and then I have I/O pins connecting to each of the connections opposite ground on the transducers. And I built it with this cable to kind of act as a general shield, and then it single-ended stuff goes back here. So I've got 2 ground pins on this connector. Let's see if I can get this. My camera doesn't stretch so far. Anyway, the 6 transducers go to pins, and then the 2 pins on the left are ground. Anyway, the principle here is that what you can do is send pulses out through these transducers, and you can phase delay them from one transducer to another. And what happens is it becomes steerable like this, right? So if let me see if I can get this thing down. If you were to fire this one with leading phase and this one with trailing phase and have them all running, it would steer the beam this way off to the left here, because this would be the first, this would be the last. It would have the effect of steering the beam. So like the Starlink internet boards, those flat antennas, they actually are 2D arrays of transceivers. So they can steer, across a 2D plane. They can move, they can point anywhere within maybe a, I don't know, 40 degree, 30 degree angle, normal to the plane of the antenna. So this thing, though, just allows you to sweep like this. Now, when you output with this phased delay, incidentally, the delay between each element is a sine of the angle times, like, I think 2.26 microseconds. So he has these things, he designed this thing very carefully. These are 40 kilohertz transducers in here, and these are half wavelengths apart, right? So from one transducer to the next, it's half of a 40 kilohertz wavelength, and there's some efficiency to be had by being exactly half a wavelength. So you can really steer this thing like this out the front. Then when it comes time to listen to the echo, what you do is you record all of your channels. And how he did it, he was writing software that would like launch a pulse on this one, then this one, then this one, this one, this one, and have them timed. And you would repeat that in a loop for like 20 cycles to make, a burst come out at an angle. And then when he wants to listen, he would start up the ADCs at the same offsets, but in reverse. Because if you send a wave out this way and it bounces back, the first transducer it's going to hit is this one, and this will be the last. So it's the same equation, just negated, so that the first is last and last is first. And then, so here's the way you read the signal coming back. This is pretty cool. You simply take these measurements off of each transducer, and then you add them together at the offset from one to another. So that what you do is you build up a composite collected waveform that would represent the angle that you're looking at, either this way or this way. Does that make sense? Imagine you've got a bunch of like sample streams, and you offset them by the phase delay from one to the other, and then you add them together and then divide them by 6, each on a sample by sample basis. And what you get is like a cumulative power sample that would represent that certain angle. Oh, and I didn't finish telling you, but the phase delay between elements, well, I think I did say, but I'll say it again, is the sine of the angle like this. So, as sine goes around 0, it's pretty much a linear situation, right? But as you get to, 45 degrees and approach 90, it becomes very nonlinear. It slows down as you get to plus minus. Where's my hand? As you get to plus minus 90, it slows down. But anyway, it's fairly linear like this. But we'll use a sine equation anyway to get the phase delay from element to element. So Dave had written his code so that he did this in PASM where he would launch a pulse and then delay, hit the next one, and loop it and do 20 of these. And I was telling him that we could do this using smart pins, right? Because it wouldn't require any PASM and you wouldn't have to have any timed code. And also he has a problem like, what if he has a very, very slight angle, right? The launch times between these become like almost 0. So you can't really discretely time that in PASM. But with smart pins, it just doesn't matter. So I'll show you how we did it in smart pins. Let me move the camera over to the scope here. Let's see. Okay, so what's happening here, this little camera never seems to want to focus quite. But it's good enough. Anyway, you can see that, let's see, it gets launched. Let's see, let me go over this way. There's 20 pulses here. So here I registered this pin here as the trigger, right? And then these are the smart pins that are generating these 40 kilohertz pulses. And these transducers are super high Q. So you put a square wave in, you get a sine wave out, you know, effectively. So the way this code works, I'll share my screen. Let's see here. If anyone has anything, just interrupt me if they want to ask or say. Share, advanced, blah. This one here. Okay. Let me shrink it down a little bit. Okay, here we go. So here's the code here. What's really doing this work is this. Let's see. Yeah, this right here is the business end. And this could even be shortened. There's some superfluous things like, see, I have 2 delays in here. This is for doing what was actually the real thing. And this is for a visual demonstration on the scope, just to show the phase delay. But here's what we do. We just pick NCO mode for a whole bunch of pins, right? So all pins, we go up here, all pins is the base pin plus 5 means it's a group of 6 pins on the same port. And we configure those 6 pins with this NCO setting, right? So we want it to always output. This is the NCO mode. Then we calculate the delay in nanoseconds. And then I do this because we loop here, we're repeating this 6 thing for each of the transducers. This is just a computation where we ultimately come up with the WX pin right here for each pin that's going to drive a separate transducer. So what we do is we come up with this this pattern of 6 offsets. And this was really important here. There's a phase setting in the NCO mode. So you can set the phase offset for any pin within a group of pins. You can make them all different. But by adding 90 degrees, which is what this does, is it kind of puts it in this clean zone where it's not going to start off with half a pulse, that all possible pulses will start from a low and then go high. So this 90 degrees buys us some like clean area to work in where we can get our phase differences. And so this is in addition to this thing right here, which we actually calculate the nanosecond difference between transducers. And then we add 90 degrees to kind of push it forward so we don't have any partial pulses. We get nice whole pulses, and then we write that. So really all this thing is doing is that this is the part that's doing something. We reset the smart pins, or we turn off the direction, right, which allows them to be configured as smart pins. We set them as NCOs. We give them a unique phase, which is in the top 16 bits right here. And then the lower 16 bits is our time base, which is 1 clock. So we want a 1 clock time base so that every clock this thing updates. So it's phase offset, plus the one clock deal. And then Y pin here gives us our NCO frequency, which is the 40 kilohertz. And that's computed, up here, right here. The NCO frequency is 40. And then this gives us our fraction for, what value we need to be adding each clock to get a 40 kilohertz signal out at the clock frequency. And then this other one here is, this is a billionth, right? It's a billionth of a second. So this is like a fraction that represents how much is 1 nanosecond in terms of the system clock. Even though the system clock is over a nanosecond, it's a highly precise value. It's a precise value that allows you to compute using this frac thing, a nice big rich number that you can use. And here's like, how long does 20 cycles take to get out, right? It's the clock frequency divided by the NCO frequency, which is this, and then divide that by 20. And I did the math in this order to keep the number of bits high to maintain good precision. Because suppose you could have just added, you could have multiplied clock freq by 20, but at higher things that may not work. It might overflow 32 bits. So works out well this way. Anyway, back down to this code here. So we reset the pins, configure them for NCO, set the unique phase up, and then we set the NCO fraction. This is going to create a 40 kilohertz sine wave. And then boom, we turn those pins low, which really makes the DIR bit high. And at that point, all those pins start outputting. And then we signal on our scope so that I can, see everything properly registered. And then I wait that 20 cycles period. Then I turn those pins off, right? And that makes them go low. And then I signal also on the scope by returning that signal low. Then we wait 500 microseconds for, this clamps the pins at ground. So it kind of it's like a ring down period on the transducer. Because those things are pretty high Q and they're going to ring like resonators. So this allows 500 microseconds. And in 500 microseconds, we're getting about 6 inches out away from the transducer. So that's enough. And then we turn the pins into ADCs. And we set up 8-bit conversions, 128 clocks. And then we enable those ADC pins. And then I have a thing that records the samples. And then the thing that does the sample strip alignment, where it does like, based on our angle, it will compute like a overall, what would you say, like a composite pattern at that, for compounding all those signal streams at that one angle of interest, so we can then get some amplitude out of it. Anyway, you can see on the scope, if you look on my little, screen where I have my camera trained, you can see that, when we put this signal high right here, that corresponds to this instruction right here, right? So those NCO pins are configured, boom, start them up. And then we're going to wait for 20 cycles to go by. So if I shrink this down and move it over this way, we'll see there's 20 cycles of 40 kilohertz there at special offsets. And then we zoom in on the back side and look, we have complete pulses, no partial pulses. Oh, look, I think there's a partial pulse. Oh, right there. I need to reduce my numerics a little bit, so I'm kind of going over. I think I could do that just if I change this. Let me see. All right, that took care of it. I just reduced it by like 2%, the excursion, and that got us clean again. So anyway, you can see it makes 20 clean, phase-controlled pulses to ring the transducers, and then it clamps it to ground, and then you can't see, but about over here or so, it goes into ADC mode, and then it starts listing for the return coming back. Any question about this so far? Did many people fall asleep? I might have. It's a lot of talking.
No, I understand what it's doing. Very Very funny use of NCO.
Yeah, see that, and I had changed the documentation because I got into this and I know I had some phase control, but I wasn't really, the documentation wasn't clear that while the pin is being held, while that smart pin mode is in reset, you can set up the phase. And then so when you turn a whole bunch of them on, they all take off with, you know, phases which they'll hold. And so you could use this for a lot of things like in group situations. So steering this beam was like an application that was useful for this kind of thing. And you see, because this is all just math that sets up these phases, we don't have any like signal launch problems like Dave was having as he coded this in PASM, where he had to start one thing and then wait so long, start another pulse, and then loop around. This is like, you know, it's perfect, and it all happens in spin. There's like no assembly language. There's no tight timing. I mean, as soon as you do this, those things start up with proper phases. It's all a single clock edge event, and those things are running and they're off to the races. And then you just do this to wait for the time to go by, and then you shut them down, and you get 20 nice phase controlled pulses.
Tip, I have a question. I missed some of this, but so sorry if you already covered it, but with like the ping sensor, for example, we had to have some power driving circuitry between the IO pin and the transducer. Do you not have to do that here?
Wait, Ken, is that you?
Yeah.
I can barely hear you. I don't know if it's
Okay.
my setup or what.
Is this better, Chip?
Yeah, a little better.
Is that better?
That's better.
Okay, yeah, sorry, if you already covered this, I had to step away and I will again, but on the ping sensor, we had to have a bunch of power circuitry between the IO pin and the transducer. Do you not have to do that with this?
So we could, of course, get a lot more output power if we did something like that, but we have really sensitive ADCs. So we may be able to get by with less power. Now, the way Dave had this thing set up, I didn't wire mine like he did, so I can't use his demo code. He actually has like a sweeping, looks like a old radar screen, you know, where the line goes back and forth and it lights up where it sees things out of the horizon. He did that, but and so I can't use his demo code because I made the cable differently. But what was I going to say about that? Anyway, he used full differential signaling on each transducer. So each transducer had two wires that would go back to two separate IO pins, and then he would run the ADCs in 100x mode differentially and just take samples and subtract, you know, the pin A from pin B, and then he would get a nice, you know, signal out of that, or a nice return signal from the transducer that didn't have any like common mode problem with any of the other pins. We could probably use like what's that? Is it Cat 5 that has like 4 twisted pairs?
Yeah, Cat 5, 5E, any of those.
Yeah, I think those would probably be good. Then with some overall shielding, probably work well on something like this. We might need 2 of those cables, but it'd be a good way to transport those signals over like, you know, a couple feet or something. But so he had really good sensitivity on the return. So you can get by with way less power on the output then. And then what he was doing is using digital IO pins in differential mode to, you know, get a 6.6 volt instead of like, you know, 3 volt, you know, from ground to power, because these are piezo transducers. So electrically, they look mostly like a capacitor would. They don't have any kind of, you know, DC impedance at all. They just have AC impedance. They don't care what their offset voltage is. So I'm just driving in between ground and 3.3 volts, but he would go like what would wind up being relative plus minus 3.3 volts. Like he'd, you know, pull one high and the other low and then flip them. And so he was getting a little more output power. but not much. But he had better sensitivity. So I started writing the code. I was up till like 4 last night, and I have there's something I'm not doing right, and I'm not getting a good receive signal yet. But he said that the receiving is like delicate. I understand the concept, but I think I probably have some problem in my code, and I might have some kind of knucklehead problem with how I'm handling the signals at this point. And I'll show you what's coming back here. If I take this off and I run, oh, and let me do this one here. Oh, and I got to go up here and change the pin to 24, not 32. So we're not going to see it on that thing anymore. So let me move my camera back. All right. Let's see. So I'll share my screen. Yeah, so here we go. So see, here's what I'm seeing. So I'm not sure why there's this initial offset. You can obviously, there's a ring with some kind of exponential decay. And if I put my hand in front of it, it does seem to act a little different. Take my hand away, a little bit different. But there's something subtle within this signal that I'm not pulling out of yet that would give us like better data about, where we are in the phased array input. So what he would do is he would output a stream of pulses at a certain angle, and then he would listen at that opposite angle because what was first is last and vice versa. And then he would add those sample streams together at those phase offsets, and then he would get kind of like a composite signal for that angle. And then he would change the angle and then repeat the process. So that's what I need to work more on that to get that thing working. And
rather than just put your hand in front of it, why don't you go to fatty material, then bone? Let's do an ultrasound on you.
Because here it is just kind of pointing out into nothing, right? And now here's my hand in front of it. Wait a minute, let me get my hand back a little bit. Okay, so my hand is in front of it.
Yeah.
Now I take my hand away. There's not much difference. Hand is in front of it. Hand is away. I'm seeing some difference, but I'm like not looking at it in the right dimension, so to speak. So it's like if you're looking, for phase and you're only perceiving power or something. So I need to like spend more time on the input side and see if I can't get this thing working like it's supposed to.
Chip, I would think your hand is, which has capacitance, is affecting the environment that it's transmitting into.
Oh, yeah. You mean if I could hold the transducer further back like this.
It's dampening the signal.
Yeah.
Okay.
Yeah.
So here we go.
So your body normally has capacitance.
Right. Yeah, I'm seeing it change a little bit, but I'm not sure. Like it's not making immediate sense.
Yeah, it's not your hand's not close enough.
So it looks like, I guess you leave the transducer charged to 0 volts after you pulse it. And then
Yeah.
the ADC tries to pull it to the 1.6 volts.
Yeah, exactly. Yeah, that's kind of what's happening. I mean, it's weird to me. I don't know why it's starting off down here. I don't know why there would be a DC offset that would persist for so long, and then it would kind of like release and then ring down. I don't know why it's doing that, but I'll get it figured out. But this is kind of a cool thing. If anyone wants one of these transducers, I can, if you get in touch with me, I can ask Dave if he'd want to create some more of these. He just 3D prints them. He spent months getting his like whole printer thing up to snuff so that he could make this part well. But he has these little transducers he just pokes in the back side, and you could wire them however you want.
Chip, I have a question.
Yep.
Is the end goal a product or just personal research, or?
That's kind of for him, just personal research, just curiosity. He's
Yeah,
very
so-
much, oh, go ahead.
Yeah, so this is actually an experiment that I have done, or so, using the Gertzel
Oh, yeah.
system. You know, so then like I was trying to do like one, you know, like one cycle each measurement. You know, and that was, you know, it worked reasonably well, or so, where I could measure like the phase of the returned signal.
Right.
But then, you know, where I kind of got stuck a little bit was trying to, you know, given like I have like one measurement per cycle, or so, I was trying to figure out, or so, well, okay, when, you know, which cycle does my real return actually start at, or so.
Yeah, it's funny, these transducers, because they're resonators. You know, you can't just, they don't turn on a dime. They're like bells that you have to ring, and then you have to dampen them, and then you have to listen if they'll start ringing again, and maybe at a different phase. They've got like a lot of what amounts to like inertial qualities.
Yeah,
I'll
so like
see.
your sampling rate, how does that compare like to the expected return time?
I am, let's see, I'm doing 1 microsecond samples. And they're 8 bits. So I'm running this thing at 128 megahertz, which is slow. But the ADCs work better at you know, like 160 meg or below. They get a little noisy as you get bigger, or as you get faster. So I'm running it kind of slowly, because I don't want the ADC noise to be contributing to the picture here. I'd like to get some variables off the table. But if you think it's like a 40 kilohertz is a 25 nanosecond period, right? And that means we have 25 samples per return cycle. But you can do, using the Gertzel, you can super carefully control. Let me see if I made a video and I put it on YouTube a while back. Let's see. Let's see if I can find it here. Propeller 2, ultrasonic. And it shows just how accurate the Gertzel can be. Oh, gee. As soon as you need to find it, it becomes hard. Let me just see if I put Propeller 2 ultrasonic. Yeah, I'm not seeing it. Let me see if I put it under P2.
Yeah, so like the
Oh, here it is. Go ahead, I'm sorry.
yeah, like this, so the sine wave, like the oscillations in that graph there, I guess that would be consistent with the 40 kilohertz.
They could, yeah, those oscillations they should be 40 kilohertz, yeah. Now you see this thing here? Let me see if I can shrink this a little bit. Oh, hold on. I want this thing to be. Hold on a sec. Okay.
From banking, insurance, and government depend on this programming language, which is
okay. Let me try to turn this thing back again.
And hardly anyone speaks about.
Okay, so there, you guys can see that?
Yes.
So here is the receiver, and I think this was the transmitter. So that thing's going at, let me run that again. So this is 40 kilohertz, and then this is listening, and the Gortzel circuit is resolving. And you can see it's like just super steady on resolving those phases.
And Chip, describe what is showing us there. Phase relationship?
In this video?
Yes.
All right, let me get this thing shrunk.
We will get to see her a lot here. Go away.
Okay.
I can't seem to get away from that video. It keeps suggesting me to watch that one.
And what
Yeah,
she's
so click
talking
that
about,
little toggle switch in the play bar that turns off to play the next video thing.
I watched
I
that
don't know why
video
they
of hers,
invented that.
and she's talking about COBOL code, which won't
Now,
go.
where's Michael Summer?
So what that is showing is the phase relationship relative to the of the receiver relative to the transmitted signal.
Right. The transmitter is on the board there. And then this is the receiver that's on a wire that's moving around.
Right. And so you
so-
can move in and out of phase and know where you are relative to the signal.
Right. Yeah. Does that make sense?
Almost. I would say you've got a really long wavelength. What frequency is that?
Every day.
Wait, what frequency is what?
You're transmitting a 40 kilohertz signal?
Yes. Yeah. So this is, can you see my little?
I can. Yeah, I can see it all there.
Okay, there's 40 kilohertz output. And this is doing Gortzel at 40 kilohertz inputting. And you can see when it stops, it's just rock steady.
Yes.
Okay, now we'll get rid of this lady here.
So something
Oh.
you mentioned a moment ago, Chip, was about the signal to noise being related of the internal analog to digital converters being related to the speed of the P2. Is that due to heating, or is
I
that
think
due
it's-
to jitter or something else?
I think it's the design. See, I never knew that the chip would run like, I was hoping we'd hit 200 megahertz. I never thought it would run at like 340 to 350. So the ADC was designed really to run at 160 because that was the target frequency of the original design of the P2 was 160 megahertz. And so the P2 was an analog. I mean, the ADC is kind of an analog thing, right? And so it was designed, I mean, I kind of simulated it at 200 megahertz, to give me some margin. And it runs fine. But when you start when that clock pulse becomes shorter and shorter, there's not enough time for the thing to settle to know if it has a 0 or a 1. And so what happens is it becomes noisy.
Ah, okay. Got it. Okay.
It just doesn't have the time to resolve, am I 0 or am I 1? And so if it was really 1, but it thought it was 0, then it's going to take maybe another couple ones to knock it back up to where it's balanced. So it becomes kind of just noisy.
And are you saying that differential kind of helps that a lot or at all or not?
Well, the differential allows you to get rid of common mode noise, right? Because let's say you send that transducer signal back in like a twisted pair to 2 I/O pins. Because you're reading those two signals differentially, there's no common mode noise with other sets of signals, or with ground, or with anything else. So it allows you just to have a quieter look at what's going on with the transducer.
Now, thinking back to your video, if I'm correct, your wavelength is about 0.3 of an inch at 40 kilohertz, right? And you were moving it an inch or two, and it was just going one phase cycle. What's that telling me?
Oh yeah, that would mean that. Let me pull that thing up again.
That kind of worries me.
Yeah.
If my math is correct, I could be wrong.
2 ultrasonic. Okay, here we go.
So we should hit 3 rotations every inch, I would think.
Right. No, what's it doing? Trouble is, there we go. Okay.
Oh, yeah. Well, it may be correct. It's hard to tell. It's hard to judge distance, but that looks like long distances.
It does. It looks like longer than the half wavelengths that Dave designed this thing for.
Right. Also, question, has Dave tested the opacity to the 40 kilohertz signal of his 3D print material?
Oh, I don't think he has.
So what's that doing to you since he's using 3D printed channels?
Right. Yeah. I mean, I don't know. This little plastic thing might convey those vibrations through it pretty well.
So you might turn all the channels except for one into listeners and transmit
I
the other
see.
and
Yes.
see what kind of effect there is.
That's a good idea. Yeah. If he were to just even because this thing is mostly hollow, right? I mean,
Right.
it's super lightweight. So,
But he's doing both lateral and vertical translations in the channels.
yes, but there's probably enough recess in there. He could just probably pour in some resin and just fill it up, and that would probably have a dampening effect.
Right. Has he shown the internal structure to you at all? Do you have a diagram?
As he was working on it, he would just kind of text me things and say, "Hey, I got this." So I'd see it. I don't have anything available right now.
So he's got eight pairs on the back of that thing, or 4 pairs?
There are 6 transducers in this thing.
So there are 6 pairs running along the
Yeah, he
length
has
of
6
those.
pairs of wire.
So what
Plus
is? Do I see 6 pairs of the circles on the back? What does it look like?
Okay,
Those
yeah.
are individual transducers.
Yeah, there's 6 transducers in there, and I have the grounds. I oriented them so there's a dot on one of the transducer legs. I figured, okay, I'll call that ground.
Gotcha.
So I oriented them I put them in the middle, and then I ran like a ground thing around here, and then the individual taps I took from the outsides.
The outer edge. That makes good sense. But that says your top row and your bottom row are 180 out of phase.
No, because
If there's an orientation in phase at all, it probably isn't.
Oh, well, yeah. Okay. So here's the trouble. He couldn't fit these things in a 6-position line, right? Because
Right, of course.
so we had to do this and then have these little tubes that feed out to the expander horns
Right.
out here. And so what I did is I looked at it this way. Now you can't see it now because this tape is in the way, but I could see that there's definitely a pattern up to the offsets. So
Right.
that, there's 3 on the top, 3 on the bottom. But if you look at it from this angle, you can definitely see who's the topmost and who's next, and bottommost.
And did he calculate the horn size for the 40 kilohertz resonance? Is that a factor at all?
Yeah, he did all kinds of. Yeah, he's really into all this stuff. I wouldn't have bothered to do so much like that, but he used a lot of theory when he made this thing.
Interesting. It'd be a lot of fun to play with for sure.
Yeah, I wanted him to come on today, but he was like, I think the idea is foreign to him, but we'll get him on at some point. He's just like the rest of us. He just doesn't do Zoom meetings, I guess.
Chip, I got a question. How about the material itself that thing is made of? Could that be affecting?
Oh yeah, I suppose this stuff, is acoustically, at 40 kilohertz, is probably, conveying vibrations to the adjacent transducers. But I think that would definitely be a case during output when you're in kind of a power mode and this whole thing's shaking. But I think that when you swamp them out and then you listen very carefully, there's probably not much coupling because the energy that's coming back into the acoustic energy coming back into this thing is so low that I think it's probably not affecting things very much. I would just suppose that's the case.
So these transducers are 6, and there's 6 outputs on the front. So you don't have a listener of any kind.
Well, we use the same ones.
Okay. as listeners as well as output.
Yeah, so first I have them hooked up in single end mode. So I go like this, 20 times, 40 kilohertz. Then I clamp it to ground. And the idea is that will cause the resonator to ring down faster than if you just let it go open circuit. Because now you've got ground and ground on either side of it. So it can't really move. So it's gonna kill that ring pretty quick. Then you open it back up again and you put it in ADC mode. And now it's like maybe 5 kilohertz impedance at 100x input mode. And so it, at that point, becomes, you put it into kind of listening mode. Now you're going to listen to see if anything comes back. And those signals that come back are many dB down than what you put out just a few milliseconds ago.
Right. This could be used for steerable audio in a sound system of some kind.
Oh yeah, and if you use 2 of these, what you could do is you could steer, and then you could have another one so that there's a point of confluence out there, and the beat frequency between them could actually have like normal human audio range program.
Right. Speakers themselves in an audio system, speakers are simply transducers.
Yes.
I mean, that's all they really are. And most of them have a given frequency range for the typical transducer used in the speaker.
Yep.
But so I'm wondering if this was kind of an application that could be used with audio in a sound system, or could it be used for something totally different? Like you do use in radar, okay? Like you mentioned something on that earlier, where you have a steerable signal that goes out, maybe running at a higher frequency range, that would send something out and you'll listen for something coming back. Or maybe one block of these works for sending a signal out, and another block of those works for something coming in to listen.
Yes. Well, yeah, that way you could decouple the transmission business from the reception business, so that you could get, like maybe you could put some low noise amplifiers on the receivers, and then use higher power on the output using some op amps or something, so that, or just some like transistor freewheeling circuits that allow like you to generate high energy pulses on the output ones without having to switch them back into low voltage listening mode.
Right.
Yeah, there'd be some advantages like that. I remember reading years ago that HP, they make these ultrasound systems, right, for medical devices. And I remember reading that, this is like 20 years ago or 30 years ago, that they'd have like 30,000 ADCs. And I thought 30,000 ADCs, but what they probably had was like, I mean, what's the square root of 30,000 here? Let me try this. I'm thinking they just had a 2D array, right? Like 30,000 and then to the power of 1/2. So that would be like 173 by 173 pixel array.
Right.
But they need that data coming in quickly, so they can do live imaging and, capture things. So that would make sense. They just have a lot of parallel ADCs on many, many separate transducers that were fabricated into a little 2D array that could fit in the end of an instrument.
With the ping, we use one transducer to send the signal and then another to receive it. But we were still having issues because the vibration goes through the PCB, and because you get the resonating frequency, so the receiver will start signaling that it will listen to the vibration, but it was going through the PCB. That's why we had to do the 2 inches or something like that blackout section where we actually shut it down. And also we use different amplification in the way back. Like we expect if the signal is close by, that is stronger. If you wait some more time, we expect the signal is going to be weaker, so we amplify more. So we have, I think, 3 sections. We have like 3 segments, and one that we void any listening, like a couple of inches. And that was because it would travel through the mechanically, through the PCB.
Interesting.
Yes.
Interesting.
Check this
And
out.
if you clamp it to a aluminum frame, does it affect it enough to matter? The PCB?
No, it didn't. I mean, it was the receiver, and the pin, they are very close together. So
Gotcha.
as soon as you fire out the transmitter, you will see the signal on the receiver.
Okay. So Chip, a separate observation. So it looks like your limitation on sensing at your current design is going to be you can't sense anything 20 pulses close to you, which means 6 inches out.
Right.
You can't sense anything closer than 6 inches, basically.
Right. There are limitations like that.
Because of your delays in your burst.
Right. Yeah, because we're using the same transducers to transmit and receive.
You have to turn around, and you're still working on the transition to receive, so you don't know what that's going to be. But currently, you're running about 16/20ths of the transmit.
Yeah, maybe like 5 milliseconds of, or maybe it's a couple milliseconds of. Yeah, the total acquisition time is 5 milliseconds. That's 2.5 feet out, 2.5 feet back.
Okay, there you go.
Approximately. So maybe a 3-foot range.
Okay.
I'm trying to find here. Let's see. He had sent me something a while back. It was really cool. It was a little circuit that kind of. Let's see. It was one of the first things he ever sent me. It was something that would drive an ultrasonic transducer and allow it to kind of freewheel, so that even from a 5-volt supply, you could get like 128 volts of swing on it. Because a lot of circuits that people would use to drive things, they would have a effective diode clamp that would go back to ground, so they couldn't really rev it up. But this thing would allow you to really crank it up, because it would cumulatively gain power as you pulsed it. Let's see. Let's see. Let me search the word piezo in here. Piezo. No, I don't see it, but he came up with a little circuit that was kind of clever that allowed you to pulse at 40 kilohertz, at the right interval, and it would just allow the transducer to get up to like 120 volts. So you get a lot of output power that way. But the thing about these transducers is you can't just turn them on a dime. I mean, even if you could, alter the phase during power output, when you're listening, you wouldn't be able to do that. It would kind of have to like go down in amplitude and then pick up again at the new phase. So there's a lot of like time constants involved in these things. It's not like a camera or something. It's like a flywheel spinning, and if you want to change the phase of it, it takes time to change everything.
Yeah, so like what if you were to clamp it to 1.6 volts using the digital to analog converter?
That's a good idea. Yeah, that's what I'll probably do next. That's a great idea. Yeah, turn it into a DAC pin, set it at like halfway, hold it there for a millisecond or so, and then, or maybe 500 microseconds, and then let it go. And then that's a great idea. That would probably, I mean, I'll experiment with things like that. Yeah, because we want to get it, we want to clamp it, quiet it down, hold it right where the ADC is going to read it, and then let the ADC read it. Oh, wait, here it is. This is it. Yeah, okay, look. This, okay, here's an article that he wrote. Let me make this thing so we can see it better. So here's typical idea, right? You take an NPN and you get some power going across it. So this thing here is like a resonator. So pretty conventional thinking here, right? So here's what he came up with. Wait, this is a little bit better. Okay, this inductor here will work in conjunction with this capacitor to form a tank circuit, but you're still going to be clamping to ground here if you try to go below ground. So what he came up with is this little bit of genius, put a diode in here, right? And now it can freewheel. So this inductor and the capacitor that is the piezo buzzer or the transducer, this forms a tank circuit that wants to resonate at 40 kilohertz. And this allows it to freewheel. So you give it ground pulses to ground in phase, and this thing can wind up being like, 120 volts across here. Does that make sense? It's like hitting the wheel every time it comes by at a certain phase. You guys can see that drawing, right?
Yes, we can. Interesting.
Yeah, so in here he has like the different, see, here's his fully freewheeling one. It's like fully AC. Here's like the other ones. Like here's one that had a tank circuit, but it couldn't freewheel. Here's the one that I think was just being pulsed to ground, and it was, you can see it wants to resonate. But when it has the diode in there, it can really generate, you can really get the power level way up. What I'll do, in fact, let's see, did he publish, how did I get this thing? Let's see. Oh wait, I gotta close this. Okay, let me get it off here.
So that was for increasing the transmit.
Yeah, that's for getting transmit power.
Okay. So
And
that
he
just
had
gives you better distance range.
Yes, that'll get a stronger signal out further.
Okay.
And then here he says the ratios. So he said this was a good way to try to read.
Still waiting for this. There it is.
Let's see.
Heck.
Yeah. He bothers to calculate all kinds of impedances and everything all the time. He's like a really disciplined engineer that way.
Beautiful.
Anyway.
But that would work well for two separate transducers. How would it work for a common one?
Say that again.
That would work well for two independent transducers that transmit and receive, but for a common transducer, that's going to be challenging to switch between the two circuit types.
Oh, right. You'd want to have, yeah, you'd almost want to have separate transducers, one that would, just do the output, and then the other that would just do the listening.
Right.
And really, I think that the way piezo ultrasonic transducers are made is they do have separate, you know, ones that are for transmit and others that are for receive. And I think the receive ones are more delicate. They take less power, but you can always use them in both directions. But they do have optimized receiver and transmitters.
Well, it's gonna be fun to see what you work out as the receive side of this. That's gonna be neat.
Yeah.
And so you're heading for what's the least amount of RCs and Ls you can use with the P2 signal processing in the smart pins to drive
Yes.
receive this. That's going to be fun.
Yeah, I think the idea of going to DAC mode and then holding it there is really cool. And see, if you have a differential pair, it doesn't matter. If you clamp them both to ground and then you turn them both into ADC,
Right.
they're going to get there together really quick. There's no capacitance to overcome.
Nice.
Anyway, we'll
You know,
get
so potentially, like, you know, if you're running 100x on the ADC or so, then, you know, it'll take quite a while to get from ground to, you know, half voltage.
right.
You know, but like what I can't really explain or so is that why we see like a waveform there or so, and why isn't it just saturated?
Yeah, the voltage I think only wants to change like following 40 kilohertz patterns, you know? Like if it needs to transition to overcome its capacitance, it's going to be inclined to want to do that, you know, as if it were ringing at 40 kilohertz. So that's, you know, 25 microseconds per cycle.
For your testing chip, have you thought of just firing up a transmitter transducer somewhere near so you can just work out the receive?
That's what he was doing when he was developing this. Yeah, I've thought of that, but I was just trying to get something quick together for today.
Gotcha.
Because he sent me this this array thing a while ago, and I had never used it yet. And I wanted him to come on today and show it, but he's like being timid, which is silly because he's like very talkative. He'll be on with us someday.
Cool. That'll be fun.
Yeah. Anyway, maybe
Any more
that's
comments?
all.
Any
Go
more
ahead.
comments? Questions for Chip? I don't see anything on the chat.
No.
All right. So Ada mentioned that she had an update from the last meeting. Is Ada still here?
Yes, I just had the mic off.
Yeah, let me stop
So
sharing. There we go.
let's figure out what's the least grungy way to share this into Zoom.
Please.
Says I need, no, I don't want, I just, okay.
Hey, Chip, while Ada is getting ready, John's asking a question.
Oh, okay.
In chat.
Oh, can we call spin to interpreter routines? From inline PASM. Probably not, because I have to think about it, but you're invoking the X byte mechanism. It might be easier just to get back to PASM. I don't know if there's any, well, no, what? You could because, well, you kind of could. You could because you can call and do a return. That's fine. But if it was relying on something being in PA or PB, like the address of where it last picked up a bytecode or whatever, or what the bytecode was, You might have to simulate that, but yeah, I don't see why you couldn't call, because all those routines terminate with the return. But they have a jump code pattern. So you'd want to like pick up that jump code pattern too. It's almost maybe more trouble than it's worth. You could use the execf instruction to get in there, where you grab the bytecode or based on the bytecode, you get the skip pattern and the jump address, and then return, because you wouldn't have one FF on the stack, you'd have your address, it would then return to you. So I think you could use the execf instruction to do that. But I don't know how many of those things would be really useful, because sometimes the compiler has to set up a pattern of bytecodes to make something work. And you wouldn't really want to do that in assembly. It'd be easier just to get back to spin and just do it in spin and then go back to assembly.
Anyways, the thing.
The simple answer is no. I guess so.
Is this smooth or is this choppy?
Well, it looks fairly good, but I'm sure it's way better on your end, because as Zoom moves the data over, it's going to have to reduce the bandwidth a bit. So it probably looks really good on your end.
Maybe if I can set on VCS I can make it twice as big, but that might help it or might harm it. I'm not entirely sure.
Doesn't look terrible.
Yeah, it does. That's what I was getting ready to say, Stephen. It doesn't look terrible.
No.
Well, because that's usually better with it not switching away from that. Yeah, this is a Tempest 2000. I've shown you this. No, why am I showing weird old games from like 1994? It's because
they're fun to play.
Somehow the source code has ended up on GitHub.
Ooh.
And you know what happens when that occurs.
It's impressive.
And well, this is running on the P2 eval right now, with the 96 megabyte board. It doesn't need that much, but I don't know. It's just what I have on the desk right now. I think the RAM that it actually needs right now is 8 megabyte, but it could probably be reduced to 4 if you wanted. The problem just is that I don't think there even is a memory way to hook up just 4 megabyte. I think they're all at least 8. So it doesn't really matter in this case. And yeah, this I'm not sure if it comes across, but it's very smooth.
It looks pretty good here, but I'm sure it's way better on your end.
Well, we'll see in the video recording afterwards if it came through well. I can try again with VCam later, which is the more traditional approach that I've been using, but that kind of causes some other issues. This right now is just so the reason the capture looks good is because I remember the funny expansion card that I waved around in front of the camera last time.
Mm-hmm.
I finally managed to get it vaguely working in a sensible way. So the number one problem is that it didn't have a PC case bracket, or whatever they call it. So if I plugged it into the computer, it would just like wobble around inside. And if you janked the cable, you could just pull it out. So I didn't want to leave it in there. I managed to very jankily fix it. It is now in there somehow, and it doesn't move anymore. The second problem is that the driver for this is it's not built into Linux. You have to download it from the website. And of course, it's janky and doesn't work with the latest version of the kernel. So I had to like patch the driver a bit to make it work, which includes, because some of the parts are like, secret, so they don't give you the source code, but they still link to like other symbols. Now they did design it in a way that would allow the stuff that actually talks to the kernel interfaces to be the parts that are not secret, that are where you get the source code. But they missed the fact that in their compiled binary module, they call a function called strlcpy, CPY. And at some point that got removed from the Linux kernel. you have to use one that's called STRS-CPI instead. So how do you fix this? You actually open it in a hex editor, the binary object, and search for the function. And because the function names are the same length, thank all deities that may have contributed to that, I can just change the byte and it will compile. That's fine. But even when the driver is loaded, it's like really picky with what applications it wants to talk to. Some of them just crash when you try to open it. So it's been a journey. But as you can see, this is very good quality. This is coming VGA right out of the P2. It can do HDMI as well, but it doesn't work with this right now due to reasons. But the VGA is really good, and that's kind of the selling point of this, is that it can do VGA captures that look basically like you're running it on the PC directly, which if you think about it, isn't actually that hard. It's just that all the cheap Chinese hardware doesn't want to do it.
Right.
A lot of this is because everyone uses laptops, so no one actually makes PCIe cards, except these weird professional companies from 10 years, 15 years ago. So what you get is you get all this compression that happens in the device that reduces the quality. As this is a PCI card, it can just it just transfers picture into the memory using DMA. And really the actual thing that does the image capture is actually, if you look on the board, there's like a big analog devices chip. And if you look up the data sheet, it's basically designed to go in like a monitor, which makes sense if you think about it, right? The monitor has to get a good capture of the signal before it processes it. And that's just what they put in there, and it works, right? So anyways, Tempest, you've been seeing me play the warp stage here. I'm gonna win the warp stage, and then I can warp 5 levels, and it's very excellent.
So Ada, you'd mentioned Linux there. Was the game this was, or the hardware this game runs on, was it Linux based?
No, I was just talking about the video capture.
The video capture. Oh, okay. All right. Never mind.
That which is why it looks so good on your screen now.
Got it. Okay.
Despite it running on the P2. But the thing this originally was for the Atari Jaguar.
Okay.
Which is utterly cursed machine. So cursed that they like sold like 100,000 or something of it, and then it like Atari went bankrupt or something. Very interesting design where basically they had a lot of DRAM in parallel to create a 64-bit bus so they can do really high bandwidth on it. And then they put the processors they connected to the bus. None of them could really do 64-bit operations very well. So most of the time it's just using like half of the bus. Utterly bizarre construction that it is.
Yeah, I remember whenever that came out, that was around the time the 3DO came out from Panasonic.
Oh, yeah. There's something very interesting. The Jaguar came out slightly after the 3DO, and it has a little bit of the original Jaguar has a little bit of an encryption thing going on, so you can't just make like a fake cartridge. Well, I say fake. It's mostly against unlicensed cartridges. I think if you cloned an official cartridge 1-to-1, it would just work. So it's not anti-piracy, it's just anti-whatever unlicensed products. So what it does is it runs some sort of encryption algorithm, and the value that it expects that it checks against is in hex 3D0DEAD. Yes, I think there's a 0 at the front as well to make it 32-bit, but
nice.
Interesting things that they put in there. I think they actually did sell less than the 3DO, which is kind of like a meme machine in its own right.
How are you?
Mostly because it does take cartridges, which is kind of an anachronism in a sense.
Yeah.
How are you piping the video into Zoom?
Right now it's this, okay, there's this utterly crustacular application called VCS, which is specifically designed to work with these data path cards. And the problem is that it doesn't really do anything. It just puts a window on your desktop, and I'm just capturing this window.
Huh, it looks really good.
Yeah, and again, it's the data path Vision RGB E1, which is like from 2009. Surprisingly, I did talk about the crazy stuff I had to do with the driver. The last update for that was like last year, like 2023. I don't know what cursed things cause it to change that much in 1 year, but yeah, this sort of thing would basically bitrot the instant that they stop the driver support. But they haven't for like 15 years, so they've got a good track record. Well, I guess you could reverse engineer the driver or something. I'm not entirely sure what the policy is for the Linux kernel. Like, how much can you look at the proprietary version of a device driver when making a open source one? I'm not sure what the rules there are, because I have sort of poked at it and discovered that the parts of the data path driver that aren't open source, you can actually, they left the debug data in, so you can actually look at the structs that they're using, which is very helpful if you're trying to figure out what it's doing. So maybe open source data path driver is a future project. But yeah, I'm trying to show off the Tempest, but we're talking about the data path that I'm using to show it. How funny.
Does it slow down when the 2000 comes up on your side?
No, it doesn't.
Oh,
But
okay. Yeah, we see it slowed down.
but
a
I
bit.
but
Probably
I do
compression is not working as well.
I get why it would slow down, because that's exactly the sort of thing that destroys video compression.
Right.
In real life, this pretty much always runs at full 60 hertz update frame rate. It does on the Jaguar, it doesn't do that really. It mostly runs around the 30 because it misses the first V blank after starting the frame. You can get this very weird effect where if you have the jump, it makes the blitter and GPU rasterize less pixels on the screen, because you're getting further away from the well, everything. Jump. Oh, I didn't change the button mapping. So if you do this jump, you know, it moves everything further away. It rasterizes less pixels. So then it just speeds the game up just that bit. Not really speeds up in the sense that it actually goes faster. It does have compensation so that when it doesn't hit the V blank, it actually runs like, I'm not entirely sure how it does it, but I guess it runs 2 simulation steps for 1 drawn frame when it notices that it can't hit it 1-to-1.
What resolution are you running out there?
This is the internal resolution is like 384 by 240, and this is the center 320 by 240 out of that, but then scaled up to 640 by 480. So that's a standard BGA signal, and
Okay.
then that gets like I made it that scaled up 2 times again to like 1280 by 960 by the VCS application. I'm not sure if that helped at all, but oh well.
So does the this is a port, right? I think last time you told us.
Yeah, this is the port. Maybe I've lost the plot because I've shown this like 3 times already in various states of completion.
Yeah, it looks a little more complete than last time. Is it? I forgot. Is it ported to 68,000 emulator on top of the P2 or?
Yes, the Well, the thing is, the Jaguar has a lot of different processors, and the 68000 in this game handles all the main logic processing. So I just took the 68000 code, relocated it to a different address because it's source code, right? Just do that and changed some other stuff around to make it work on the P2. But then the code runs through the 68000 emulation. Just because that's kind of already there. That was kind of like the easiest way to make it going, to get it going. I think that was like the first thing I got going. It worked immediately without problems. So yeah, that's just the easiest way to do it. As you can see, it works fine enough. There's no need to make it any faster. And if anything, there are avenues to make this faster, but I think the biggest thing probably is to make the text routine double buffer the data that it loads from the external memory. Because the way it's currently doing that, it will ask for the data for one line of the letter, and then it will just wait for it to come back. Whereas there should be enough memory to double buffer it so that it reads the next line of the text and then it, you know what I mean, right?
Yeah.
So that it can parallelize that. I think for the text and also for these big explodey graphics, they use basically similar code. Messed up the easiest warp stage. They use similar code, the text and the explodey things. If you couldn't tell, what doesn't use similar code is all the other sort of little pixel explosions. They actually use a completely separate thing because they are not bitmaps that are being drawn. It's just drawing like rings and spheres of pixels. Also, as you could just see when these exploding text things happens, these exploding bitmaps, they actually are positioned in 3D space. So when the camera zooms back out, the thing also gets smaller. I don't know why it is like that, but it's very strange. And yeah, this is very, very nice, I think. Interestingly, all the graphics processing is just happening on one cog. There's another one that does the that like composites some stuff around, but that's mostly needed because of how this is written. Just how the original is to you'd have to change a lot more if you wanted it to work differently. So it needs that other cog to composite multiple buffers together. So like the score and the live counter is on a different frame buffer. And so that needs to be plumbed through so it shows up on top. But really all the actual pixel plotting happens on one cog. And this is this looks pretty good and runs at high refresh rate. So that's kind of a good show of what's possible, I think, if you extrapolate that.
Yeah, after going through emulation.
I mean, the graphics aren't emulated. The graphics are native code. I think I've shown that on the last episode or the one before that. The sort of process. I take the original microcode assembly. I open up a new section in the propeller file next to it, and then I just like translate the instructions across. The instruction set isn't all that different, so oh no, I'm died. Oh no, I'm not dead. I have cheated death. And also now I have the AI droid, the only good AI, because he shoots down geometric shapes. But he is a geometric shape himself. What an ethical disaster that is luckily avoided by the AI droid being an unthinking cold machine.
All right. We are 2 hours into the live forum. Chip, I think you need to go and take some rest to keep going with your
Oh yeah,
Brazilian research.
Yeah.
I only got like
Anyways,
4 hours of sleep.
parting words is you can find this on a thread on the forum, but the real thing is on GitHub.
Ada, good work.
Yeah, that's pretty cool.
Actually, building this is like a minor hassle because it needs like the 68000 assembler and linker. So you kind of it kind of just works if you do it, but if you do it right, but you need to do it right. That I have instructions that work on Linux, on Ubuntu Linux, anyways. But who knows if anyone can even get this to build on a Linux system. Technically, you don't need to even build the 68000 part because that one is independent of any P2 hardware changes. That's just a blob that gets loaded into memory and then executed.
I got a question. Has anybody done 4-bit SDIO yet?
Oh, for like SD cards.
Yeah.
I think I mentioned that earlier. The one guy on the forum is like working on that. Has been for a while. I think the thread pops up from time to time. It says something about 4-bit SD card accessory board or something.
Okay. I thought Roger was working on that.
Oh, the other guy, I forget the guys. Let me check in on the guys. This is not the right thing. This is the right thing.
The last forum thread I saw was pages and pages and pages and pages.
Yeah, I mean that's what a good forum thread is.
Yeah, I know, but it takes
Oh.
takes a bit to catch up. So that's what I thought I'd just ask before I spent hours reading all that.
See, I think
All
as I
right.
recall, he was just trying to tweak the speed and everything on that to figure out what the limits were.
I think
At
he
least that's
hasn't even done writes yet. At least from what I last remember. He's just been focused on reading now. But the writing is its own thing because I don't think you can turn off CRC in SDIO mode. So you kind of have to calculate the CRC of what you're sending.
Okay, let's go into the open discussion. Let's end the recording here. A little over 2 hours.
Hopefully not.